Hello and welcome to our project introduction video. In the next few minutes, we'll take you on a journey to region retrieval in digital pathology with whole slice image. I'm Zhao Liu Ziyu. Well, first, let's start with some backgrounds on WSI. WSI is a high-resolution imaging technology that digitizes tissue slides using automated microscope scanning systems, enabling detailed observations at magnificence like 4x, 10x, and 100x on a computer. Unlike traditional microscopes, WSI provides seamless zooming between broader tissue context and fine cellular details. It supports tasks like cancer diagnosis, biomarker research, and education, enabling researchers to analyze large data sets and identify real histological patterns. However, WSI pose unique challenge due to their size, complexity, and information distribution. Well, let's explore 5 key issues using a visual example. Well, now you can see in this platform, this is a breast cancer tissue cell slides, and we will use this visual example to illustrate the 5 key challenges in WSI. The first challenge is scale too large. You can see WSIs can span palace, making traditional image processing method inefficient. And the second challenge is multi-granularity information. You can see WSIs contains high rational details across varying magnifications, requiring a sophisticated multi-scale analysis. And the second challenge is sparse information in patches. For example, the white part patterns. Many regions of WSIs lack relevant data, so necessitating efficient focus on key diagnostic areas, maybe some red areas. Yeah. And the fourth challenge is tissue is non-object. Unlike natural image, WSIs lack distinct object, making traditional detection method unsuitable. And the fifth challenge is uneven information distribution, which means diagnostic regions vary in density, meaning that models must prioritize meaningful areas effectively. Yeah. This challenge has driven researchers to develop innovative solutions, and one of the most advanced is UNI, a groundbreaking pathology image encoder published in Nature Medicine this year. UNI leveraged extensive datasets encompassing a wide variety of diseases and species, making it highly versatile in pathology applications. Well, its training process is built on a powerful Dino framework, which employs a dual branch architecture, a student branch and a teacher branch. This structure enables the model to effectively align and interpret image information, resulting in a deeper understanding of complex pathology images. Well, according to the experimental results presented, UNI consistently outperforms other models, and it performs well in key downstream tasks such as classification, segmentation, retrieval, and recognition. These achievements highlight the potential of UNI, and our project is inspired by this work.
So I'm Su and I will introduce our pipeline and the improvement of WSI region retrieval. In our pipeline, there are 2 parts in our workflow. So in the first part, as the WSI that we have, we will slide the WSI into patches and use them to pre-build a vector database to support the semantic retrieval on the patches level. And for the patches, we will use the image encoder, which is the UNI that I've introduced before. And we will build them as a vector database with their vector and their current and their information with the payload, which means that the patches size, the patches position, and the patches level, and to build them based on the QDrown vector database, and to build the index to them. So with the patches level vector database, the second part of our workflow is to build a retrieval process to use the patches retrieval and the query region that users provide to find the retrieval result from our source WSIs. So we will selection the query patches from the query region and use these patches to trigger the basic patch retrieval and to rebuild the region on the current WSIs. As the detail of our retrieval process, when user provide a query region images, we will slide it with a grid to get the anchor patches of a query region. So based on these anchors that we choose, the basic patches retrieval will get many retrieval result decrees for each query anchor, which consists of the latent result. And based on these results, we will find the source WSI with the voting, just like the green patches, because they are point to the same source of WSIs, and their numbers are the first in these results. And check their adjacent relationship and get the region candidate, which means that the black box is the patches position, and the red box is the region that with their adjacent relationship, that we rebuild their region based on them. So in the end, to fit the shape of the query region, we will reshape the region candidate with the size of the query region and return as the result to the users. So based on the basic patches retriever, we build a region retrieval process, but it still has many aspects that we can optimize and improvement. So first, for the patch storage, as we mentioned before, the WSI information is imbalancing in many cases. So we want to only storage the useful information and to filtering the sparse information patches, which can help us to get more efficient retrieval on the patch level, which also can reduce the storage requirement. So based on the current research, we use the O3 algorithm to binarize the thumbnail of the WSI and use the ratio of the white pixel corresponding to the patches to determine whether it's a background or it's a foreground. So the O2 algorithm is to use the pixel intensity to determine one binary threshold to change the RGB feature into the black-white into the binary feature, and we use this kind of binary thumbnail to check the patch white pixel and black pixels ratio to determine whether it's a background or foreground for one setting threshold that we are given to determine these things. When the ratio of the white pixel corresponding to one patches is larger than this threshold, we will consider it's a background, since there will be more useless information in these patches. Otherwise, it's a foreground. So by only saving the foreground images, we can reduce the storage space requirement while preserving the patches with the valid information. So this is the first improvement of our whole process. The second improvement point is that we try to reduce the anchor that trigger the patch retrieval through the clustering. Since patches with a small distance usually have the similar semantics, so we try to find some represent anchor on the semantic level to trigger the patch retrieval will be more efficiency. It's more reasonable. So in here, we choose three kinds of clustering method to help us to get the represent anchor, which is the k-means as the usual, and the k-means plus, and the EM algorithm based on the Gaussian mixture model, and to help us to choose the represent anchor. And we will discuss the efficiency of our region retrieval process. The third improvement is the post-processing of the region retrieval region, since we might have some shifting on the query region and retrieval region to more accurate, elegant the information between them. We use the ORB feature, which is the oriented, fast, and rotated brief descriptor, to elegant the two regions, only based on the information of the color and the shape from their images itself, to efficiently and accurately retrieve the region results. So here's the whole process and some improvement of our WSI region retrieval process, and Haiqi will introduce our experiment and visualization result in this case. Here, so this class, the basic region retrieval, is the function that we realize. And there's some module that's not in this file, but we only need to show their main process. So when users are given the images, we will get the width and height of the images, and we will slice it into patches. The raw result will be get with the single retrieval, and the target of the WSI name and target result will be found based on the results, and the region result will be checked their elegant result, just as we mentioned before. And as the final result, target WSI name and redefine the region will be provided by the user. So when user will to choose a region on the WSI, and the backend will detect the position XY on their left top point, and the width and the height and which level this WSI, and the whole process will to retrieve from other WSI and to get the results.
From now on, I'm excited to share our experiment result. Our goal was to validate the workflow and assess the performance of improved modules for patch level retrieval. We selected 20 whole slide images from the TCGA BRCA dataset, extracting approximately 60,000 image patches. These patches were encoded using the UNI method and stored in an ORAN-based vector database, enabling efficient retrieval. For the experiment, we used a randomly selected region from WSI as the query, with the slide name serving as the ground truth label. To evaluate performance, we relied on two metrics: cosine similarity to measure feature similarity, and the intersection over union called IOU to evaluate the overlap between the query and the retrieved region. Our results revealed several key findings. First, by adjusting storage thresholds, we observed the trade-off between storage efficiency and retrieval accuracy. For example, a lower threshold of 0.86 reduced storage by 81.4%, but results in a retrieval success rate of 61.5%, while a higher threshold of 0.98 achieved a success rate of 73.6% with a reduced storage compression of 63.5%. Second, we compared the performance of K-means, K-means++, and the EM algorithms. K-means++ stood out, achieving the highest average similarity score of 0.539 with a runtime of 4.528 seconds. Lastly, increasing the number of matched patches denoted by K significantly boost retrieval success rate. For instance, raising K from 10 to 30 improved the success rate from 0.4 to 0.7. Lowering similarity thresholds further enhanced accuracy, with IOU and cosine similarity scores reaching their peak at the threshold of 0.7. The visual example on the slide illustrates the retrieval results, showing the query region alongside the retrieved region. The patch statistics below provide additional insight into the retrieval process. In conclusion, our finding highlights the importance of balancing storage efficiency and retrieval performance, optimizing algorithm selections, and tuning parameters like patch counts and similarity thresholds to achieve high accuracy. This slide demonstrates an example of the region retrieval results from our experiment using TCGA BRC dataset. The query region extracted from a whole slide image containing 40,000 patches is shown on the left. On the right, we present the top-ranked retrieved regions sorted by their cosine similarity scores, which measure how closely the retrieved regions match the query. The highest-ranked result with a similarity score of 0.9587 shows a strong resemblance to the query. As the similarity scores decrease, for example, 0.8116 and 0.6758, the retrieved regions become progressively less similar, which align with their ranking. The lower-ranked results, such as the one with the similarity scores of 0.2939, show significantly reduced relevance. Links to each retrieved regions are provided below, allowing for detailed inspection of the results. This example illustrates the effectiveness of the retrieval system in identifying and ranking regions based on their similarity to the query, with high-ranking matches clearly correlating with visual similarity. This slide shows how anchor points are selected using two clustering methods, K-means and EM clustering. On the left is the query region, which contains the pathological features. The middle panel shows the K-means results, where the region is split into clusters with different colors. The red points mark the anchor points, which represent each cluster and are important for retrieval. On the right is the EM clustering result, which creates more flexible cluster shapes because of its probabilistic approach. The anchor points in EM are better aligned with the natural distribution of the data, while K-means produce simpler, more rigid clusters. The comparison shows that the K-means is faster and easier to use, but EM clustering gives more accurate results. Choosing the right method depends on the task. And this slide illustrates the process of region image alignment, showcasing how the system retrieves and aligns a region from the database to match the query region. On the left, we see the query region, which contains distinct pathological features that serve as the input. In the middle, the retrieved region is shown, representing the best match identified by the system based on the similarity matrix. On the right, the aligned region demonstrates the result after applying alignment parameters to adjust the retrieved region to match the query region. The green outline highlights the alignment boundary, showing the precision of the alignment process. The alignment parameters listed at the bottom include transformations such as translation, scaling, and rotation. These adjustments ensure the query and retrieved regions are optimally aligned. This visualization underscores the effectiveness of the retrieval system in not only identifying the more similar regions, but also aligning them accurately from meaningful comparison in digital pathology tasks. In conclusion, this project successfully established a fundamental pipeline for region retrieval in pathology WSI images, leveraging a vector database and a state-of-the-art image encoder to enable efficient patch-level retrieval for region retrieval insights. To enhance the retrieval process, the project introduced three key optimizations. The first is the database size reduction. The OSDU algorithm was applied to binarize the thumbnail images, distinguishing cached patches from the background patches. The second is the query anchor selections. Cluster analysis was performed on the query regions patches to select representative patches as query anchors. Finally is the region alignment. ORB feature were employed to align the query region with the candidate region. The experimental evaluation validated the effectiveness of the basic region retrieval workflow. Thank you all for your time and attention. My name is Lin Haiqi. I appreciate the opportunity to share our work and look forward to any questions or discussions. Thank you.